Have you ever stopped to think about what everything around you is actually made of? I mean, really made of? We're about to dive deep into the fundamental principles that govern every single material in the universe. We're talking about the atoms themselves, and more importantly, the bonds that hold them together. This isn't just theory. This is the absolute bedrock of material science and all its applications. So, to get started, let's jump right into a really fascinating puzzle, something that gets right to the heart of what materials science is all about. I like to call it the carbon paradox. Okay, just look at these two things. On one side, you've got graphite, the stuff in your pencil. It's soft, it's dark, you can write with it. On the other side, a diamond. It's literally the hardest natural substance on Earth, it's transparent, and it's a terrible electrical conductor. But here's the mind-blowing part. They are chemically the exact same thing. Both are 100% pure carbon. So how on earth can the same exact atom build two materials that are complete and total opposites? Well, the answer, and this is really the main idea for our whole discussion, is that it's not about the ingredient, it's all about the recipe. The secret isn't the carbon atom itself, but the architecture. It's how those atoms are arranged in space, and crucially, the kind of connections or bonds that hold them together. You can think of it as the fundamental source code that dictates every single property a material will have. Right, so to crack this code and really solve our carbon paradox, we have to zoom in. I mean, way, way in. We need to get a good look at the fundamental building block of all matter, the atom. Okay, quick refresher. At the heart of the atom, you've got the nucleus, packed with positively charged protons and neutral neutrons. The number of protons, that's the atomic number, or Z, is what makes an element what it is. Carbon will always have 6 protons. Period. Add in the neutrons and you get its mass. But honestly, for us, the real action is with the electrons, those tiny negatively charged particles zipping around the outside. They're the social butterflies of the atom. They're the ones that interact, form bonds, and ultimately define a material's personality. Now, how do we picture where these electrons are? Well, the old school Bohr model on the left thought of them as little planets stuck in these neat, tidy orbits. It's a simple picture and still useful sometimes. But today, we know the wave mechanical model is much closer to the truth. It sees electrons less as tiny dots and more as probability clouds, showing where you're most likely to find one. But here's the key takeaway that both models agree on. Electron energies are quantized. That's a fancy word, but it just means they can't have any random amount of energy. They have to exist on specific energy levels, kind of like rungs on a ladder. You can be on one rung or the next, but you can't be in between. This is a non-negotiable rule, and it's the foundation for everything else. So if electrons are stuck on these specific rungs, how do we keep track of them? How do we find the unique address for each electron so we can figure out what it's going to do? We do it with something called quantum numbers. Just think of it like a mailing address. You've got 4 of them. The principal quantum number, N, is the big one. It's the energy shell, kind of like the state or city. Then L tells you the shape of the orbital, that's like the street. ML gives you its orientation, which is the house number. And finally, MS, the spin, tells you if the electron is spin up or spin down. And the Pauli exclusion principle is just a simple rule. No 2 electrons in the same atom can have the exact same address. But for us materials scientists, the most important electrons, the real VIPs, are the ones on the outermost shell. We call them the valence electrons. These are the frontline soldiers, the ones that actually do the bonding and basically control everything. All right, we've got a handle on the atom itself. Now, what happens when 2 atoms get close to each other? Let's talk about the fundamental forces that govern how they interact. It's really this elegant dance of push and pull. As 2 atoms approach, an attractive force starts to pull them together. But if you push them too close, their electron clouds start to overlap and they repel each other, just like trying to push the same poles of 2 magnets together. A stable bond only forms at that perfect sweet spot, the equilibrium distance, where the pull of attraction and the push of repulsion perfectly cancel each other out. The net force is 0. That's the happy place for atoms. And this curve right here is basically a cheat sheet for understanding that balance. Seriously, this is one of the most powerful tools in material science. You see that dip at the bottom? That's the lowest energy state, and it happens at the exact same equilibrium distance we just talked about. Now check this out. The depth of that well tells you the bond energy. A deeper well means a stronger bond, which means a higher melting point. The steepness of the well tells you how stiff the material is. A really steep, narrow well means you need a ton of energy to pull the atoms apart. That's a super stiff material. And finally, see how the well isn't perfectly symmetric? That slight lopsidedness tells you how much the material will expand when it gets hot. It's amazing. So much information about a material's properties is packed right into this one simple curve. Okay, so atoms find a stable spot to form a bond. But how do they actually do it? Let's dig into the three main recipes that atoms use. And of course, it all comes down to those VIPs, the valence electrons. First up, we have ionic bonding. This is a story of give and take. You've got a metal, like sodium, that has an extra electron it would love to get rid of. And you have a nonmetal, like chlorine, that's just one electron short of a full shell. So what happens? Sodium just gives its electron to chlorine. Now you've got a positive sodium ion and a negative chloride ion, and opposites attract. This attraction is really strong, and it's non-directional. It pulls equally in all directions. The materials you get from this, like ceramics, tend to be very hard but also brittle. And because all the electrons are now locked in place, they're fantastic electrical insulators. Next up is covalent bonding. The motto here is sharing is caring. Instead of one atom giving an electron to another, two atoms decide to share their valence electrons to make both of them stable. Now, this is key. These bonds are highly directional. It's not a general attraction. It's a very specific, locked-in handshake between atoms in a certain orientation. Think of diamond structure. It's a perfect example. Because these bonds create a rigid, interlocking framework, covalent materials can be incredibly strong. This is the bond you'll find dominating polymers and semiconductors. And just like ionic bonds, the electrons are pretty much stuck in these shared bonds, so these materials are usually insulators too. And finally, we have metallic bonding. Now, this one is the real wild card of the group. In a metal, the valence electrons basically decide to leave home. They detach from their original atoms and form this mobile sea of electrons that flows around all the positive metal ions. This electron sea acts like a super strong, non-directional glue holding the whole thing together. And this model perfectly explains why metals are, well, metallic. That free-flowing sea of electrons is why they're amazing at conducting electricity and heat. And because the glue is non-directional, the atoms can slide past each other without breaking the structure. That's why metals are ductile and malleable. You can bend them and shape them. Okay, so we have ionic, covalent, and metallic. The giver, the sharer, and the commune. Three totally different ways of holding things together. So let's put them head-to-head and see how they really compare. This table just lays it all out perfectly. It all starts with what the electrons are doing. Ionic bonds transfer, covalent bonds share, metallic bonds delocalize. That one fundamental difference creates a cascade of consequences. Look at directionality. Covalent is super directional, the other two aren't. That leads directly to their mechanical properties, the hard, brittle ceramics, the super strong covalent materials, and the ductile metals. And finally, conductivity. Are the electrons locked down or free to roam? That determines if it's an insulator or a conductor. You can see this perfect logical line connecting the type of bond directly to the type of material. All right, we have covered a ton of ground here. The atom, the forces, the bonds. Now it's time to zoom back out and put it all together. Let's see how all this tiny atomic-level knowledge helps us make sense of the real-world materials we use every single day. So here's a really important reality check. We've been talking about these bonds as if they are three distinct, separate boxes. But the real world is almost never that neat and tidy. The truth is, most materials have a mixed bonding character. They don't fit perfectly in one box. They exist somewhere on a spectrum between these pure types. And this bonding triangle is the perfect way to visualize that spectrum. Think of it as a map of all materials. In the corners, you have your pure bond types. You can see metals clustered down in the metallic corner. Polymers are way up in the covalent corner. And ceramics live along that edge between ionic and covalent, which tells you they're a mix of both. Then you have fascinating materials like semiconductors, which live somewhere in between. This map is incredibly powerful because it lets us classify almost any material and start to predict its behavior just by seeing where it sits on the landscape. Which, of course, brings us full circle. We started with a puzzle, and now we have all the tools we need to solve it. Let's go back to our old friends, graphite and diamond. And here it is, the big reveal. In diamond, every single carbon atom is locked into a rigid 3D network with 4 other carbons using those super strong covalent bonds. It's like a jungle gym built by giants. There are no weak spots. That's why it's so incredibly hard, and why electrons are trapped, making it an insulator. Now look at graphite. The carbons also form strong covalent bonds, but only in flat 2D sheets like layers of chicken wire. And what holds those layers together? Practically nothing, just some incredibly weak secondary forces. This means the sheets can slide right past each other, which is why graphite is soft enough to write with.
Plus, some electrons are free to zip around inside those sheets, which is why graphite can conduct electricity. It's the same atom, but a completely different blueprint, a different architecture, leading to a universe of difference in properties. So, let's wrap all of this up. What's the big takeaway? Why does digging into this atomic-level world truly matter? Not just for understanding things, but for actually building the future. Here's the bottom line. There is a direct, predictable line from a material's atomic blueprint, its structure and its bonds, to the large-scale properties we can actually see and use, like its strength or its conductivity. And once you understand that relationship, everything changes. We can stop just finding materials in nature and start designing them. We become material architects. We can predict and engineer brand new materials with exactly the properties we need for things like better batteries, faster computer chips, or stronger and lighter airplanes. Understanding these bonds is the absolute key. It's how we're going to build the world of tomorrow. The question is no longer just what can we build, but what properties will we choose to engineer into the very fabric of our world.